All right. Way back at the start of 235, we talked about reactions of conjugated dienes. One of the first ones we did was 1,2 versus 1,4 addition. This is actually kind of a fundamental concept, but we use it again when we do Michael additions later on. The observation was if you have a conjugated diene in the presence of HBr, you can add to the first two carbons as one isolated double bond, or you can do a 1,4 addition. The mechanism of this, we're basically going to protonate. We're going to protonate in order to form the most stable carbocation if you have a choice. Markovnikov style. Recall that the carbocation we get is going to be resonance stabilized between positions 2 and 4 relative to wherever you put the proton on. The 1,2 and 1,4 addition simply results from addition at either of these carbons. This is 1,4, and this is the product that we get. We said the trends. 1,2 tends to form rapidly at low temperatures. 1,4 is predominant at higher temperatures. And even at low temperatures, 1,4 will predominate if you give it enough time. What that means is that we're forming 1,2 rapidly, and that 1,4 is the more stable product. So it's an equilibrium. We can do addition and elimination, and eventually work ourselves to the 1,4 addition product. We tend to call these types of products either thermodynamic or kinetic. Thermodynamic means we're dealing with the most stable product. Kinetic means this one's formed faster. Again, the rationale, this is all reversible. So we form this guy, the 1,2, rapidly, and very slowly we work our way down to 1,4, which accumulates because it is more stable. Any question on the concept? As you do these types of reactions, remember, you're going to protonate to form the most stable carbocation. And then you're either going to add 1,2 or 1,4 relative to the protonation. Let's go ahead and do a set. Just quickly jot down the products of these reactions. You'll note that I'm either asking for 1,2 or 1,4 products. The question that you need to ask, once again, is where do you put the proton to give the most stable carbocation? In the first one here, if we put the proton on this carbon, on this end, the carbocation will form here at the second or tertiary center, and that will be the most stable carbocation we can form. If we're doing simple 1,2 addition, we're going to add, there's the carbocation we form. For simple 1,2 addition, we'll just add the bromide anion to that, and the product should look like this. Any questions? Most stable carbocation, and then add the anion. If we did a 1,4 addition here, we would still add to this carbon down here, and we would still form exactly the same carbocation. However, for 1,4, we remember that this is in resonance with the carbocation out here. And for the 1,4 addition, we simply add bromide to this carbon on the end. The final product should look like this. Here we have a cyclohexadiene. We're going to do a 1,2 addition. The ring isn't substituted, so it doesn't really matter where you put the proton. Let's just put it up here to form this as our carbocation. The proton went on here. Bromide is going to add to this position right here. And this will be our 1,2 addition product. For the 1,4, we're going to do exactly the same process. Just going to put it at either end here, doesn't matter. Put it at the top, form the same carbocation. Remembering that this is now in resonance with the carbocation down here. If we added here, we would get the 1,2 product. Here is the 1,4 product. And it would look like this. It is, of course, exactly the same as the 1,2 addition product. Any questions? We also did our favorite reaction, every organic chemist's favorite reaction, and that is the Diels-Alder reaction, a 4+2 cycloaddition, where we take a diene and a dienephile. When we do this, we form a simple cyclic alkene. It's 4+2, so the ring that we form will be an alkene with 6 carbons. Now, of course, we can have substituents out there, which makes this much more interesting product. The way this thing works, it's a concerted cycloaddition. We make all of our bonds at the same time, something like this. And these guys shown in red here are the bonds that we made in this reaction. This is also called an electrocyclic reaction. Again, it is concerted and no intermediate. We go directly to the product. Any question? The challenging thing about doing Diels-Alder reactions is drawing the products when we have polycyclic rings involved. This was the first one that we looked at. Once again, let's just take this apart. For our cycloaddition here, these are the 2 bonds that we made. Looking something like this. 6-membered ring with a double bond. Now that's the very, very classic one. Go ahead and draw the cycloaddition product for cyclopentadiene and ethene. As you do this, what you need to remember is that the carbons of the dienephile, so ethene in this case, are simply going to add to the end carbons of our diene. So the bonds we're going to form are going to be like that. And once again, it's a 4 plus 2, so we're going to make a 6-membered ring. But because we have a 1 carbon bridge here, there's going to be a bridge sticking out from our 6-membered ring. Product, this is our diene half right here. This is the rest of our 6-membered ring. So we have a 6-membered ring with a double bond, and here's our 1 carbon bridge sticking out. If I color it, looks like this. Once again, these are the bonds we made. Here's our dienophile, and this is the diene. Oops, this wasn't supposed to show, so pretend the answer isn't up there. Once again, we're going to take the carbons of our dienophile and simply add them to the end carbons of our diene. When we do that, these are the bonds we make. This is our dienophile right here, and this is the carbons from our diene. Any questions? Next, we moved on to benzene and benzene-like compounds. We talked about aromaticity. We just did 4 plus 2 cycloadditions. Well, this is the 4n plus 2 rule for aromaticity. Remember what Huckel suggested was, if we have a pi system where we have continuous conjugated sp² centers, and in this system we have 4n plus 2 electrons, where n is any integer, except here, we can expect a special stability. The stability is described as aromaticity. Again, it must be a conjugated pi system. It must be planar. That pi system must contain 4n plus 2 electrons. If you do that, you wind up with an aromatic system that's very stable. If you have all the criteria met, except the Huckel number, so you have the wrong number of electrons, that's exceptionally unstable, and that's actually referred to as anti-aromatic. So let's just look at some examples. If we start off with our first one, it is planar. It's a square, it has to be. It has conjugated double bonds. However, it's what it looks like in a model. It has 4 pi electrons. 4 is not a Huckel number, so this is not aromatic. Since all the criteria are met, this is an example of something that is anti-aromatic. We can see that if we look at the electrostatic potential map. We do have nice pi systems here for both of our double bonds. However, they're not overlapped into a nice conjugated system that we would expect for benzene or whatever. Speaking of benzene, that was our next one. Here we have 3 double bonds. Each of them contributes 2 electrons. So this is 2, 4, 6. 6 is a Huckel number with n equals 1. So benzene, of course, is aromatic. That's where the whole concept came from. And this is what a nice aromatic system should look like. Very delocalized, beautiful little thing. Our next guy on the list was cyclooctatetraene. Now, a cyclooctatetraene has 2, 4, 6, 8 electrons. If you do the 4n+2 rule, this is not a couple number. Cyclooctatetraene, however, is not anti-aromatic because it actually looks like this. It's not planar. We can't squish these guys out to make them flat, and so it's kind of a basket sort of case. It's a basket case. The electrostatic potential map looks like this. We have electrons for all of the double bonds, but of course, because it's not planar, it cannot be aromatic. The next one on the list of compounds we looked at was the cyclopentadienyl anion. So here we have 5 carbons in a row, in a ring. We have 2 double bonds, and what we've done is pull a proton off of our CH2 here. That leaves it as an anion. Now, originally, this would have been an sp cubed carbon, because that's what carbanions are. However, this molecule can achieve great stability if it takes these electrons and then rehybridizes so that each of these centers is sp squared. When we do that, we'll have 2, 4, 6 electrons. It looks like this, a beautiful anionic aromatic compound. And of course, everybody's favorite is the tropylium ion. Tropylium ion, you learn to draw a 7-member ring. Always a challenge. Here we have a carbocation in our ring. We have 3 double bonds, that's 6 pi electrons. We can delocalize this positive charge over all 7 carbons. This is a Hubble number of 6, so that's good. Nice and planar, and it's absolutely a gorgeous, stable aromatic system. Any question on the concept? Aromaticity is a concept. Once again, for cyclobutadiene, 4 pi electrons, it's anti-aromatic. Benzene, of course, is aromatic. Cyclooctatetraene, we said, was basket-shaped, so it is not aromatic, has the wrong number of electrons. Cyclopentadienyl anion is planar, has 6 electrons, and of course, so does tropylium. Any questions? Just make sure you understand the concept of aromaticity. This is the anion is a particularly interesting one because remember, the carbanion here would normally be sp cubed, but it rehybridizes so that we have sp squared centers at all locations, and that makes it aromatic. All right, next, we moved into reactions of aromatic compounds. The first thing we looked at was simple reactions of side chains. This is a very, very simple reaction. We're taking permanganate anion, and basically if you take any substituted benzene, as long as it has a 1 benzylic hydrogen, permanganate in water, warm it up a touch, will all give benzoic acid. Only requirement is that we have at least 1 benzylic hydrogen. What happens to all the rest of the stuff? Well, this just washes down the sink. Let's just do a couple quick examples. Take these two compounds and draw the products from permanganate oxidation. All you have to do here is convert the benzoic carbons into carboxylic acids. Here we have 1,4-dimethylbenzene, also called paraxylene. If we take this and oxidize it, we wind up with paraphthalic acid, benzene 1,4-dicarboxylate. If we have this guy, once again, we're going to split at both benzoic carbons, and we wind up with phthalic acid itself. So that's benzene 1,2-dicarboxylate. Any question? We also looked at another reaction of benzoic hydrogens. Way back when we did alkenes in chapter, whatever, 6, 5, whatever, we talked about allylic bromination. Well, remember, the allylic and benzylic positions have very similar reactivity for the same reasons. They form very stable radicals, very stable cations, etc. If we do N-bromosuccinimide in the presence of a radical initiator, we wind up brominating in the allylic position. Let's go ahead and very quickly just jot down the products for our allylic bromination. All we're going to do here is take off a benzylic hydrogen and replace it with a bromine. In this case, toluene gives benzyl bromide. Now the problem with these types of reactions, of course, is that the radical that you would form from benzyl bromide is actually more stable than the benzyl radical. So we can get polysubstitution. You have to very carefully monitor your conditions in order to get monobromination. Here we have a propylbenzene. We're going to brominate in the allylic or benzylic position. And once again, nothing happens to our ring here. We're just going to pull off the benzylic hydrogen and stick a bromine on. The key to understanding this is we're going to form the stable benzylic or allylic radical, just like back in organic 1. There was one more really kind of neat reaction called the Birch reduction that we did, where we took a benzene ring and did a dissolving metal reduction. Now, we've talked about dissolving metal reductions again last semester. Here we're using lithium. You can also use sodium. And you do this in liquid ammonia. Lithium and liquid ammonia, we form hydrogen radicals. It's a radical reaction. The neat thing about it is that we wind up with the non-conjugated diene. So we go from benzene to the 1,4 diene as opposed to the 1,2. Go ahead and finish the set here. just remembering that when we have substituted benzene, the Birch reduction places a double bond on the ring carbon, which is attached to an electron donating group. What that really means is that the methyl and the methoxy are going to be at these centers of at least one of the pairs of double bonds. For our first one, the product is going to reduce so that we wind up with a double bond attached to our methyl group. And the same thing here with our methoxy group. Double bond is going to look like this. If you have electron withdrawing groups, the reaction either won't go at all, depending if they're really badly electron withdrawing, or the electron withdrawing groups would be here, not on one of the alkene carbons. All right, so take our compound here and very quickly draw the products for N-bromosuccinimide, radical bromination, permanganate oxidation, and Birch reduction. For our first one, because we have two benzylic positions, we can brominate in both places. If we have enough bromine there, we'll add this to form this guy. If we have an excess of bromine, we'll actually make the tetrabromo product. If you don't have enough bromine, you would just put one on. For our oxidation, once again, we're simply going to split at the benzylic carbon. Each benzylic carbon becomes a carboxylic acid. And finally, the Birch reduction. Alkyl groups are electron donating, so we expect our double bond here to be bridged by our cyclopentyl group here. Any questions? Well, these were reactions of side chains. We also looked at perhaps one of the key reactions of benzene derivatives, and this was electrophilic aromatic substitution. Here we're going to take a benzene ring and we're going to substitute it. We're going to substitute it with a halogen. Halonium ion is our actual electrophile here. We said we could do nitration, where we have NO2 plus as our electrophile. Sulfonation, where we have protonated SO3 as our electrophile. The FRIEDEL-CRAFTS alkylation, using a carbocation-like species to put an alkyl group on the ring. And finally, acylation, where we use an acylium ion, again, as our electrophile. Now, for electrophilic aromatic substitution, because it is a key reaction in organic chemistry, it is important that you understand the stepwise nature of the reaction. So let's just look at this. First thing we're going to do is make our electrophile. When we add bromine, halogen in general, we use conditions where we have bromine or chlorine, whatever, in the presence of a Lewis acid. very common Lewis acid would be something like iron 3 bromide. So bromine, in presence of iron 3 bromide, we form a bromonium ion-like species. Now this is going to come and sense the huge electron density here of our pi cloud. We're going to form a pi complex, but that is rapidly going to rearrange. Oh, we could also use aluminum bromide. That's going to rearrange to a sigma complex that looks like this. Now what we've done is simply add the electrophile to the ring. When we do this, of course, we destroy the aromaticity. So this ring is no longer aromatic. That's an important multiple choice style question. The intermediate in electrophilic aromatic substitution is not aromatic. In order to regain the aromaticity, we have to lose the hydrogen on this carbon bearing the electrophile. When we do that, we regenerate our 6 electrons in our pi system, and we have a substituted benzene. This, of course, works equally well with something like chlorine, iron 3 chloride, or aluminum chloride. The intermediate is always going to be the same. The halonium ion-like species is going to add to the ring. It is no longer aromatic. We lose the hydrogen, leave the electrons behind, and get chlorobenzene. Now again, this is a standard mechanism question. Make sure you understand the addition, elimination nature of this reaction.
Is the final product considered aromatic?
Yeah. The driving force for loss of the proton here. This isn't a very acidic hydrogen, is it? The driving force is that we go way downhill energetically to make the aromatic system. For nitration, the mixture you actually use is nitric sulfuric acid, both of them concentrated. It's a very, very powerful acidic solution. We dehydrate nitric acid and make NO2+. That's our electrophile. Just like every other thing, the electrophile is going to add to the ring to form a sigma complex that is not aromatic. We're going to lose the hydrogen. In this case, we would simply make nitrobenzene. You can do this reaction several times. If you had toluene as your starting material, you can nitrate it 3 times, and that makes trinitrotoluene, or TNT. Very, very simple to make. Sulfonation. Again, we're using really nasty acids here. This is sulfuric acid with SO3 dissolved in it. Called fuming sulfuric acid, nasty stuff. Protonated SO3 is our electrophile. Same sort of addition product. Once again, we're going to lose the hydrogen. We make the sulfonic acid. Now the FRIEDEL-CRAFTS reaction. This is really a very important reaction in organic chemistry. Make sure you understand what it is. In the FRIEDEL-CRAFTS alkylation, we take our Lewis acid, and because we cannot form a free carbocation with something like a methyl group, we actually, this is the complex that serves as the electrophile. So the bromine coordinates with the iron. We get something that looks like this. This behaves as if it was a carbocation. And because of that, it can add to the ring. We form exactly the same addition intermediate, rapidly lose our hydrogen, and we have just made toluene. Remember, in the FRIEDEL-CRAFTS reaction, you need the Lewis acid because we really can't form the free and clear carbocation. The whole complex is what reacts. The acylation. Oh, okay. Reaction is limited to alkyl halides. If we have double bonds or whatever, it doesn't work. If we have electron withdrawing substituents on our ring, it doesn't work. We can often get multiple substitutions. Now that makes sense because once we put an alkyl group on, that enhances the reactivity of the ring, doesn't it? So we can stick another one on and another one even more easily. And finally, because we have a carbocation-like intermediate here, we can get rearrangements. This is a real bummer because it makes putting straight chains on the benzene ring very difficult. We can get around some of that using the FRIEDEL-CRAFTS acylation. The acylation, again, our Lewis acid will coordinate, but now we're making an acylium-like ion. The acylium ion is much, much more stable than a carbocation. And because of that, this is kind of floating around more or less free. Has a real lifetime in solution in water. Something like this would have a lifetime of about 10 to the minus 9 seconds. So it's a real intermediate. This again is simply going to add to the ring. When we lose our hydrogen, we have made a ketone. The nice thing about this reaction is that because we have a very stable acylium ion, we do not get rearrangements, we do not get multiple substitutions. Again, we can't do this if we have electron withdrawing substituents on the ring, but for other things this works very, very nicely. Instead of using an acid halide, we can also use a simple acid anhydride. Any questions? Well, let's just look at a couple. Go ahead and quickly draw the products for these electrophilic aromatic substitution reactions. Chlorine in the presence of iron 3 chloride. Chloronium ion is going to be our electrophile. We lose our hydrogen, and we would simply make chlorobenzene. Remember, SO3 in the presence of concentrated sulfuric acid forms protonated SO3. That is our electrophile. Benzene sulfonic acid is our product. This last one, I threw in an acid anhydride just so we could do that. It makes it look a little different. In the presence of aluminum chloride, some Lewis acid, we are going to form an acylium ion. Remember, we're going to lose the carboxylate half of this thing. So this is going to be gone, and we're only dealing with the acylium part as our electrophile. This is going to add, and we're going to form the propan-one derivative. We also talked about substituted benzenes. Remember, just like we said, alkyl groups and things that can pump electrons in by resonance are going to activate the ring towards electrophilic substitution. It makes sense because it's electrophilic, isn't it? Anything that pushes electrons in is going to make it more reactive. Turns out that this includes everything from the halogens on up, and because of that, we wind up with ortho-para-directing groups. Remember, if we pump electrons in by resonance, those are going to wind up with electron density ortho and para to our substituent. That's why we direct to that position. If we have electron withdrawing substituents, we're removing electrons from the ring. That makes them deactivating relative to benzene. If they are deactivating, then by resonance we have lower electron density, ortho and para. That's lower electron density. That means that the only place you can stick something is metal. It's still a lousy reaction, but that makes them meta-directing. Pushes electrons in, gonna go ortho and para, pulls electrons out, only place left is meta. Any questions? Let's quickly just do a quick problem set. All alkyl groups are electron releasing. The process is referred to as hyperconjugation. Basically, you're going to increase the electron density ortho and para to the alkyl group in the presence of chlorine, iron 3 chloride. We would make the simple fluoroisomer. This is fluorochlorotoluene. We also get orthoisomers too. If you look at your list, sulfonic acid is electron withdrawing. That means this is going to be poorly reactive. The electron density, ortho and para, to the sulfonic acid group is decreased by resonance. Because there's less electrons there, the only place you can put something is meta. The king of deactivation is the nitro group. Nitro group really is very effective at removing electrons by resonance. So we're real electron deficient, ortho and para. We can iodinate in this case, but again, we only get meta isomers. Another set. Well, I guess these really isn't another set. The only one that's different here is this guy down here. So let's go ahead and put these back. This guy here, we're doing a FRIEDEL-CRAFTS acylation, aren't we? Using an acid halide. Aluminum chloride is our Lewis acid. The acylium ion is going to be this half of the molecule. We are activating here. This is a fairly big group, the isopropyl group. Because of that, we're pretty much going to stick this thing only in the para position. It's just way too crowded here. Ortho. Again, a simple FRIEDEL-CRAFTS acylation. The important things to remember about electrophilic aromatic substitution is the nature of the mechanism. Make sure you can draw the intermediate for the electrophilic addition. You need to understand the driving force for the loss of that proton, and that is to regain aromaticity. We're looking for electrons in this reaction. The electrophile is. Therefore, if we have electron donating groups on our ring, we're going to go ortho and para to those, and that's where the electrons are by resonance. If we have electron withdrawing groups on our ring, the only place we have to put something is going to be meta, because we have depleted the electron density ortho and para. Any questions? Well, after we finished reactions of benzenes, we moved in to alcohols. We looked at a bunch of reactions that yielded alcohols. This is simply borohydride reduction. Sodium borohydride, very nice, very simple product to use. Does have some drawbacks, but it's soluble in water. Again, it's a very, very simple reaction. All we're going to do is donate a hydride anion to the carbonyl carbon. When we do that, because it's a hydride anion that puts electrons up on the oxygen, that picks up a proton from the solvent, and we get the alcohol. Go ahead and just jot down the products for these two remaining reductions. Yeah.
So after the first step, it would just be a cyclohexene with an O attached with one
O
bond?
minus, right.
Okay.
Because remember, you're adding H minus.
Yeah.
So
That's
zero
like the
charge,
intermediate stuff?
this is an O minus.
Okay.
If we take benzaldehyde and do this, we are adding our hydride to this carbon. That makes it a benzylic carbon, and we simply wind up with benzyl alcohol. Acetophenone, just going to add it here. We make the 1-phenyl ethanol as our product. Now we looked at a more powerful reducing agent. More power is good. The problem with being more powerful is if you have multiple functional groups in your reaction, you can also reduce those at the same time. In terms of making alcohols, however, lithium aluminum hydride in ether works very nicely. Lithium aluminum hydride, we remember, will flame spontaneously in moist air. Since you're doing this in ether, which is an explosive solvent, this makes it really a dangerous reaction, something you want to play with. Once you're done with your reduction, you dump it into aqueous acid carefully, and that gets rid of everything. The nice thing about lithal is that in terms of alkenes, it is much more specific than borohydride. If we did this reaction with borohydride, we would reduce the carbonyl, but we'd also largely reduce the double bond as well. With lithium aluminum hydride, we keep the double bond, and we simply get reduction at our carbonyl. Because this is an ester, in our addition intermediate, we're going to do two steps. Our first is going to put a hydride here. We still have a leaving group now for methoxide. That leaves, and we put a second hydride on. The rule to remember, if you are reducing an ester to make an alcohol, you always will wind up with a primary alcohol. Esters, lithiol, primary alcohol. We can reduce ketones. If we reduce the ketone here, all we're going to do is convert this to the alcohol. I believe this is called borneol, natural product. And if we take phenylacetic acid, again in the presence of lithiol, we're going to reduce our carbonyl twice. Going to add 2 moles, just like we did with an ester. OH is our leaving group, just like O-methoxy was here, or O-methyl. And we wind up with a primary alcohol. So the words to remember, if we have an aldehyde, we will get a primary alcohol. If we have an ester or an acid, we will also get a primary alcohol. If we have a ketone, we get a secondary alcohol. Now we're going to revisit lithium aluminum hydride a little bit later when we do nitriles and things like that. Any questions? The really classic way in organic chemistry to make alcohols is our Grignard reaction. Make sure you understand about the Grignard reaction. Again, this is one of the key reactions of the semester. Make sure you get this one. Cycloaddition, electrophilic aromatic substitution, Grignard. In our Grignard reaction, we have an alkyl or aryl or vinyl halide, and it's going to react with magnesium and ether to form the Grignard reagent. In the Grignard reagent, the alkyl group has anion properties. It looks as if it's an anion. You can just simply imagine these things as, in this case, the methyl anion adding to the carbonyl carbon. When we do that, we simply make the alcohol. Here's our color-coded piece. We would add them like this. This is the bond. The black bond is the one that we made in this reaction. Simply methyl anion adding to the carbonyl carbon. Like I said, we can also make a Grignard reagent with a aryl halide, in this case, bromobenzene. This is going to react as if it's the benzene anion. Again, it's simply going to add to the ketone carbonyl here. Notice the aldehyde up here gave a secondary alcohol. The ketone is going to add, and we're going to form the tertiary alcohol. Our last one here, we have a cyclopentanone methyl group here adjacent to the carbonyl. We're going to once again generate carbanion character here on our secondary carbon. That's going to be our nucleophile. These are going to add, and we're going to form something like this. Any questions? Now we're generating a stereocenter here. We can actually make both enantiomers because it just simply depends on whether we attack from the top or the bottom. Now, one of the things that we want to do is to use this chapter to develop our synthetic skills. Take each of these compounds, take these reaction conditions, and go ahead and draw an appropriate starting material. Carboxylic acid we could reduce to make this, an ester, etc. I will pause for a moment while you synthesize. This is a primary alcohol. We're doing it from a carboxylic acid. The carbon that bears the OH, well, that used to be the carbonyl carbon, didn't it? It was a carbonyl carbon of a carboxylic acid. So all we have to do is use this carbon, make it into a carbonyl, and start off with benzoic acid. We're adding 2 moles of hydride to the carbonyl carbon to make the primary alcohol. Esters are also going to add 2 moles of hydride. Once again, this carbon, the one bearing the OH, was originally our carbonyl. What was the alcohol portion? I don't have a clue. Anything you put down would work. This is going to be our carbonyl carbon. All we need is an alcohol of some sort to complete the ester. Now, just like we can add 2 moles of hydride to an ester, we also add 2 moles of Grignard to an ester for exactly the same reason. Get the intermediate, lose the alkoxy group from that intermediate, and then add again. What you need to do is to look at this and decide what bonds, what 2 bonds we made in our Grignard reaction. The 2 bonds, well, this used to be the carbonyl, didn't it? We know that. It's an ester, so attached to this carbonyl was an alcohol portion of some sort. We don't know what it was, we don't care. Also attached to the ester carbonyl was a hydrogen. That means that the rest of this, the whole 6-membered ring, came from the Grignard. We're adding it twice, so we've added once to the carbonyl, twice to the carbonyl. This is a combination that would work. So things to remember. When we are adding hydride, lithium aluminum hydride adds twice to carboxylic acids, adds twice to esters. Grignards also add twice to esters. Now, one of the neat things that we learned about the Grignard reaction is that there are 2 pathways to prepare an alcohol from a ketone or aldehyde from a Grignard reaction. There are always going to be two pathways. So let's look at this molecule here. Again, this is one of the skills that you need to make sure you have. Take this molecule and come up with two Grignard syntheses. Very classic question. What you're going to do here is simply say to yourself, here's the OH group. That used to be a carbonyl, didn't it? You know that. So, we've either added to this side of our carbonyl or to the other. So, mentally you want to take and split on one side or the other. If we split here, then we have added our benzene ring. That means that this used to be the carbonyl compound. Because it has a hydrogen attached, it's a secondary alcohol, it was an aldehyde. So our Grignard reagent was simply phenyl magnesium bromide, and all the rest of this was our carbonyl compound. The set would look like this. Again, we know it was an aldehyde because it's a secondary alcohol. Now that's one pathway. To get the other pathway, we just simply split at the other side. Now the carbonyl is on the left portion of our molecule, and this stuff over here was added by the Grignard. Go ahead and draw the carbonyl. Again, it's going to be an aldehyde. And draw the structure of the alkyl halide that we use to make our Grignard. The aldehyde simply add a benzene ring, carbonyl carbon, and hydrogen. That makes it benzaldehyde. The Grignard reagent itself, we add a halogen of some sort here in carbon 2, so this would work as our Grignard. Any questions? Once again, being as blatant as I can, this is a standard sort of question. Make sure you understand how to take, split it open, and choose both reagents, both sets of reagents to make something. Well, let's apply this to synthesis in yet another fairly standard test question. Here we have a set of potential starting materials, and we have a target molecule. Now, the simplest thing to do here is just to look and say, okay, well, wait a minute. We have a benzene ring. So from our set of starting materials, we actually only have 3 guys that have benzene rings in them, don't we? So this somehow makes it all a little simpler. We have to come up with a synthetic approach that's going to start with these 3 guys, into these guys, And we're going to have to add a substituent. So here's our bromine. And we're going to have to make a benzyl alcohol. And most importantly, they're going to be meta to each other. Now we're going to have to add something to the ring. We know that a methyl group is going to be ortho-para-directing, isn't it? So we're not going to wind up with a meta product. Forget that one. Our bromine is also going to be ortho-para-directing. However, the aldehyde group is electron withdrawing, therefore it is meta-directing. So pretty much this says we're going to start here with benzaldehyde. Everyone understand the logic? All right, what we have to, oops, that's what to happen yet. What we have to do is somehow introduce our halogen. We know electrophilic aromatic substitution allows us to introduce a halogen meta using bromine and iron 3 bromide. That would give us our 3-bromo benzaldehyde. Again, logically, once we have 3-bromo benzaldehyde, we can take and simply reduce the carbonyl to a CH2 using either lithiol or borohydride. Our first step is simply going to be the bromination of benzaldehyde to give the 3-bromo benzaldehyde. And our second step is simply going to be the reduction of the carbonyl to the primary alcohol. You can do this either with borohydride, which is safer, or you can do it with lithium aluminum hydride. The key thing to do, the key point of this, the key logic step, was to realize we needed an aromatic compound. We needed to wind up with meta substitution, and only one of these will direct meta. That's the key logic. Any questions? Let's do another one with this set. Here we're going to make a secondary alcohol. Now we've seen there are ways that we know to make secondary alcohols. We can take a ketone and we can reduce it. We can also make a secondary alcohol from a Grignard reaction in an aldehyde. We are dealing with an aliphatic compound, so we need to look up top and see things that have simple chains. We can rule out all these compounds with rings, really, and our double bond. Really, we're just dealing with these 3 compounds as potential starting materials. Now this guy down here, the alcohol, looks so promising because it's like half the molecule, isn't it? But we don't really know a reaction that's going to let us stick this 3-carbon chunk just directly onto that alcoholic carbon. We don't know that. So that's not going to work. This is ethyl formate. We know that Grignards will add twice to an ester. So in ethyl formate, this would be an OH group, and we would carry on with the hydrogen. Up top, we have ethyl 1, 2, 3, 4 butanoate. Now, that's half of this molecule, isn't it? However, remember the ester portion also carries over. So instead of making a secondary alcohol, this would give us a tertiary alcohol. The one that's going to work is going to be the ethyl formate. Remember, the group that's attached to the ester, this guy or this guy, is going to survive. What we need here is the hydrogen to survive, and we need to add Grignard twice.
On that top left one, wouldn't that, couldn't you add a Grignard and get rid of the ester as a leaving group?
But
and then
that
do
would
the
give
same
us-
thing?
But that would give us the ketone intermediate. And that's going to then add a second mole of Grignard to give the tertiary alcohol.
But if there's not a, but there's only one here that can leave, right?
Well,
Would that stay?
this guy leaves,
Yeah.
and we're left with carbonyl, 3-carbon chain, and another 3-carbon chain.
So one.
But in the presence of Grignard, this is going to add again. So instead of a hydrogen here, we would have a 3-carbon chain. So these are the bonds we made in our Grignard reaction. We're dealing with ethyl formate as our starting material. We simply need a 3-carbon Grignard, and we can do it that way. Grignard reagents are very important in organic chemistry. Make sure you understand the logic of how to do a Grignard synthesis and pick out an appropriate starting material. Again, if you don't see this yet, work through it. The ester up top here would give us a tertiary alcohol, because whatever's attached to the ester, hydrogen or the propyl group, survives. You need the hydrogen, not the propyl. In the chapter on alcohols, we also looked at simple reactions. This is the Williamson ether synthesis, where we're just doing an SN2 reaction using the alkoxide anion as our nucleophile. Just like we learned back in Organic 1, this is an SN2 reaction, works best on primary or allylic carbons. We need something with a leaving group. We could either use a tosylate, toluene sulfonic acid, or a simple halogen. Go ahead and just quickly draw the ethers that we make from these Williamson reactions. Classic reaction from Organic 1. All that happens is the alkoxide anion attacks, in this case, the benzylic carbon. Bromine leaves, SN2 reaction. This is the bond we just made, and we make the simple ether. Phenoxide is also a very suitable nucleophile. Again, the oxyanion will attack our CH2 group. Bromine is our leading. There's a bond that we made, again, between the methylene cyclopentane and phenoxide. And then our last one, we're using cyclopentanol anion as our nucleophile. Tosylate, OTS for O-toluene sulfonate, standard leading group in organic chemistry. This will attack the CH2. The tosylate leaves as a toluene sulfonate anion. All we do is make our bond here, and that's our product. Now in our chapter on ethers, which we just made, we learned that ethers are, in general, dead-end products because they really don't do much chemistry. They're just not very reactive at all. You can kind of reverse this reaction with HI, concentrated HI in heat, drive it back, make an alkyl halide and an alkoxide. But that's, again, just the reverse of the Williamson synthesis. There were a couple exceptions of ethers that, in fact, were reactive. However, epoxides are the classic examples here. Epoxides are reactive because our three-membered ring is highly strained. Because it's strained, it will ring open very easily. You can also ring open four-membered ethers, four-membered rings. Fives are too stable. But threes work best. What you're going to do in this reaction, again, is an SN2. In the SN2 reaction, all you're doing is taking our nucleophile and you're attacking the one of the ether carbons. When we do this, we're going to follow the general rules for SN2 reactions. In this reaction, we have a benzylic carbon and a CH2. Our point of attack here is going to be our CH2 in the ring. That's simply because, even though the benzylic carbon, we always think of that as being reactive, this is just crowded as all get out, isn't it? One of the most important things to remember about SN2 reactions is steric hindrance. We shoot for the least hindered target. All we've done is take the isopropyl group, add it to this carbon, we ring open, this is now the alcohol, this guy here, this guy here is the bond we just made. We've added the isopropyl group, these two were the carbons of the epoxide. We can do the same thing just with simple acid hydrolysis. Here we're going to protonate the ether, makes it even more reactive. Our nucleophile is going to be water. When we do this, because it's an SN2 reaction, our attack is going to be from the backside. That means that we're going to wind up with a 1,2 diol, but because it's a backside attack, our stereochemistry is trans. Remember, 1,2 diequatorial is trans. This is kind of a neat reaction because if we had an alkene and we used permanganate or osmium tetroxide, we would get the cis stereochemistry. If we convert that alkene into an epoxide and then hydrolyze, we get trans stereochemistry. Our last example here, instead of using the Grignard anion as our nucleophile, we're going to use alkoxide as our nucleophile. Same thing, anion attacking, SN2 reaction, look for the least hindered target. In this case, it would look like this. We've added the alkoxide portion here, so these two carbons and the oxygen are what we added. These two carbons here were the epoxide. All right, to kind of summarize up the chemistry for the alcohol and ether chapters, let's just do a couple very simple synthesis. These are going to be 2 steps. As always, you look at your starting material and say, what in the world is it? You take a peek at your final product. Take a peek at your starting material. Pick out the portions of that that are going to wind up in this, and then work yourself backwards. As we look at this, we say this is an ether, isn't it? We know how to make ethers really one way or so, and that's going to be through a Williamson ether synthesis. That's the simplest way. Williamson ether synthesis, we're going to take an alkoxide and react it with an alkyl halide. We could have methoxide as our alkoxide, but then we would have to introduce a leaving group here, a couple carbons away from our ring. That's going to be more difficult. If we split on this side, then we'd be dealing with this as the alcohol, and we're simply adding the methyl group. So once again, there are 2 ways you could do this, but adding the methyl group is going to be the simplest. Go ahead and draw the structure of the alcohol. And you're going to use something like bromomethane as your electrophilic agent. The alcohol has all the carbons of our final product, except this oxygen was an OH. We convert the alcohol into an alkoxide. Here I use sodium amide, nice strong base, no problem. That makes alkoxide. Here I dumped in iodomethane, bromomethane would also work to give the appropriate ether. Now, our synthetic problem has shifted. Now we look at this intermediate, we look at our starting material, and we say, how can we convert benzyl bromide into this alcohol? Well, what we want to do is look and say, well, it is a secondary alcohol, isn't it? We know we can make secondary alcohols with a Grignard reaction. It has to be a Grignard with an aldehyde. So you want to look at this material. Obviously, our alkyl halide is going to be our benzyl bromide, isn't it? Here's the benzene ring, here's our CH2. So this part here came from our benzyl bromide. This part here came from the aldehyde. So quickly draw the structure of our aldehyde. The aldehyde only had 2 carbons. Where the oxygen is was a carbonyl. There's a hydrogen attached because it's an aldehyde. And it simply is acetaldehyde. So step 1, we convert benzyl bromide into a Grignard. Step 2, react that Grignard with acetaldehyde or ethanol. We make this alcohol, convert it to the oxyanion, and do a simple Williamson ether synthesis. Any questions? All right, let's do a similar sort of synthesis here. Again, let's start with benzyl bromide. And we're going to make 1, 2, 3, 4. That's 4 phenyl 2-butanone. 4 phenyl 2-butanone. So it's a ketone. Now, in terms of making ketones, we know that we can make a ketone if we have an alcohol. The alcohol is the alcohol carbon will be the one that is the carbonyl here. And we do that by a simple oxidation reaction. Now, there are a couple ways that we learn for oxidation of alcohols. We can use chromate reagents, and that works okay if you're careful. We can also use pyridinium chlorochromate. It's a chromate reagent, but it's very, very selective. You can even make aldehydes with it. Can't do that with just plain old chromate. So if we look at this, we could say as our first step, it's a ketone. We could make that by oxidation of a secondary alcohol. So go ahead and quickly draw the structure of the secondary alcohol. And again, you want to either use simply chromate, chromic acid, or PCC, pyridinium chlorochromate, as your oxidant. Well, the structure of the alcohol is trivial, isn't it? This just used to be an OH. So all we have to do is draw this. Again, put in an oxidant of some sort, convert the alcohol into the carbonyl. All right, now our synthetic problem is simply this guy. We look at it, and once again, it's a secondary alcohol. We're going to make that by a Grignard reaction. The problem is that we have benzyl bromide as our starting material. And so that's this many carbons. But we have an extra carbon, an extra CH2, that's somehow crept in our molecule. So what we're going to have to do is use this as our Grignard, and we're going to have to add it to something that's going to make our secondary alcohol. The only reaction we know that's going to do something like this is going to evolve an epoxide. So our Grignard reagent is simply going to be our benzyl bromide. This is the bond that we would make if we were doing a simple addition to acetaldehyde, but that one doesn't work because, again, we need an additional carbon here that we don't have. Therefore, what we're going to have to do is this. This is the bond we have to make with our benzyl bromide. And again, this chunk used to be an epoxide. It's the only way we know to introduce the extra carbon. So, go ahead and draw the structure of the epoxide that we would need to do this. The epoxide must have had 1, 2, 3 carbons. We made this bond, so this and this were the epoxy carbons. The oxygen was bridging these 2 carbons. And the stuff simply must look like this. Again, attack at the least hindered carbon. This is the bond we make. 1, 2, 3 carbons, 1, 2, 3, and the alcohol. Any questions? Well, after we finished with simple carbonyl compounds, we moved into more recent work that concerned carbonyl condensations. An example of a carbonyl condensation that we looked at was the aldol. In an aldol condensation, what you're doing is taking an aldehyde or ketone, you're taking 2 of them. You're using base to convert the alpha carbon into an enolate anion. That's our nucleophile for our second mole of Grignard to give, our second mole of aldehyde in this case, to give product. So step 1, we enolize 1 mole with the base to form the enolate anion. Enolate anion is going to be our nucleophile because the electrons in the oxyanion can move down to the alpha carbon. That's going to then attack the second mole of aldehyde or ketone. And when we do that, we get, this becomes an OH group. I'm sorry, this is a carbonyl. This becomes the OH group. And we get the beta hydroxy aldehyde. The bond that we made here between our carbonyl carbon, so it's this one, we have 2 carbon aldehyde and a 2 carbon aldehyde. Now, all of the condensation reactions that we looked at basically are going to follow this same mechanism. The one thing that confounds it a little bit is that sometimes the enolate anions that we use can undergo decarboxylation as a second step. Okay? But the guts of the reaction are going to be just like the aldol. We're going to make an enolate anion that's going to attack a carbonyl. Classic one that decarboxylates. Well, one of the classic ones is the Claisen condensation. In a Claisen condensation, instead of an aldehyde or ketone, we're using an ester. The mechanism, however, is going to be exactly the same. Step 1, we're going to take this and enolize it. The enolate anion is our nucleophile. This anion is going to collapse, electrons move up, and attack the second mole of ester. Exactly like we did with aldol. This gives us this intermediate. Now, this is a standard classic azotransfer intermediate, isn't it? We have a tetrahedral intermediate, and we have a leaving group attached. Our leaving group is ethoxide, and if you notice up here, our solution is swimming with ethoxide. So it's a very fine leaving group. When this tetrahedral intermediate collapses, the electrons will move in, ethoxide will move out, and we wind up with, in this case, ethyl acetyl acetate. Now we'll talk about the decarboxylation of ethyl acetoacetate later. But this is the classic Claisen condensation. Just like the aldol, same basic mechanism, except we're using esters instead of aldehydes or ketones. That's important to remember, okay? Typically, you do a Claisen between two small molecules. There's a specialized reaction called the Dieckmann condensation, where you do this to form a cyclic product. All it is two esters in the same molecule. Again, the mechanism is going to be exactly the same. We're going to enolize one of them. Enol is going to collapse. We're going to form a tetrahedral intermediate. This is going to eject methoxide, which we have in our solution. And again, we wind up with a beta ketoester. It's just a specialized version of the Claisen. Sometimes on multiple choice tests especially, you'll see the word Dieckmann condensation is nothing more than a Claisen that yields a ring. Any questions? All right, we'll return to decarboxylation in a minute. Before we do, let's just visit the Michael reaction. This goes back to the very first sets of first slides that we looked at in this review. Instead of using a diene, however, for 1,2 and 1,4 addition, we're simply using a conjugated ketone or aldehyde for our 1,2 addition reaction. These are referred to as the alpha and beta carbons. Once again, we can form these two resonance stabilized carbocations. If we did addition to this, which would be equivalent to 1,4 addition, we would just get a simple carbonyl tetrahedral intermediate. We've already done that. If we add here to this carbocation with the nucleophile, something like this, we wind up with nucleophile added to the beta carbon. So let's review the reactions that we know that undergo simple Michael addition. We said we could add cyanide using either HCN or the reagent of choice is actually diethyl aluminum cyanide. What happens is simply cyanide attacks our beta carbon and we form the addition intermediate. Simple Michael style addition. We also saw that dialkyl and diaryl copper lithiums can add to our beta position. And then what is actually the original Michael reaction, amines also add to the beta position to give, in this case, a secondary amine. Now, we were talking about anions derived from enolates. Turns out that we can also do the same reactions here with an enolate anion. We made, well, this is methyl acetoacetate, make that from a chlysine. This is dimethylmalonate, the dimethyl ester of malonic acid, and this is malononitrile. All of these are going to form very stable anions on our central CH2 here. And all of those anions can be used as nucleophiles for a Michael addition. Now these molecules get a little bit scraggly, so go ahead and draw these things out just so that you can make sure you see where you're going to form these bonds. In our first one, the anion is here in our central CH2. That is simply going to add to the alkene carbon here, give a 1,2 addition, hydrogen here, all the rest here, and it would look like that. The bond we made is this guy here between dimethylmalonate. These were the carbons of our original alpha-beta unsaturated carbonyl. With malononitrile, the reaction is exactly the same. This is our anion right here on the CH2. It's going to add to the beta carbon. Bond that we made is this one here. Again, this part of the molecule is from our starting ketone. And with methyl acetoacetate, same thing. Enolate anion is here on the central CH2. That attacks our terminal carbon. Again, these are the same carbons. These guys are all the same. This is the bond that we made. Any questions? Now, there are actually just two more nucleophiles I want to talk about. This is an enamine, isn't it? We made this from a carbonyl compound and this 5-membered cyclic amine, piperidine it's called. It's an enamine because it's an alkene where the nitrogen is directly attached to it. This is a nice stable form for an enolate anion because the electrons move in and we get electron density here. This guy we didn't talk about too much, but it's in your book. Nitromethane, nitroalkanes. We know that the nitro group is very, very electron withdrawing. And because of that, we can form a carbanion on the alpha carbon to that. This is sometimes a useful reaction. The product of this case would be this. The 2 carbons of, well, the 1 carbon of our nitroalkane is simply this guy, and the rest of this comes from our alpha-beta unsaturated ketone. Now, what's happening here, oh, okay, let's back that up then. I thought I lapsed to the other slide first. What happens here is that this is our anion, and it's going to add to this carbon. So we get one of these complex looking intermediates. But in the second step, we're going to dump in acid. When we do our addition here, remember this is an ammonium cation, which we then hydrolyze to a ketone. Product is going to look like this. These are the carbons of the enamine, and this, of course, is our starting ketone. Let's go ahead and look at the mechanisms of these just to make sure we understand it. Nitromethane, any nitroalkane, will have electron density alpha to the nitro group, simply because we can pull the hydrogen off and form this intermediate. In the reaction we just did, this electron density is going to attack the beta carbon. We move the electrons up to form an anion. When this anion collapses, it will pick up a proton here. And our final product is the nitrocarbonyl compound. The lesson here, I suppose, is that nitroalkanes, nice electron density, and they're good Michael reactants. Everyone see where this came from? Our second product here was our ketone. Remember, we're going to do this because we have electron density here. The enamine, nitrogen, the electrons are going to come in, electrons will attack. Our product is going to look like this. Now our enolate, of course, is going to pick up a proton right down here. So we wind up with this as our intermediate. But in an enamine reaction, we have the imine, the ammonium ion, as our product. When we dump this stuff into acid, the imine hydrolyzes and generates the carbonyl. So both of these are a little more sophisticated examples of Michael addition, but again, they all involve electron density, attacking the beta carbon, collapsing our enolate. In this case, we have a hydrolysis step. Any questions? All right, well, let's do one of these addition reactions that's multi-step and bizarre, involving a Michael addition of methyl acetoacetate. Here I'm going to do 4 separate steps. We're going to, number 1, do our addition. Now we know that. We know what's going to happen. The anion is going to attack beta. We're going to get some intermediate. Our second step, we're going to take and acidify that, warm it up a bit. Our third step, we're going to dump in base. Oh my goodness. And then our last step, we're going to acidify again. So let's just follow this along and see what we would get. Our first step, the anion is going to attack and do a Michael addition. This is our anion, where the electron density is, going to attack beta. There's our anion. Anion is our nucleophile at the beta position. And we get one of these strange-looking intermediates. Everybody should be happy with that. Now the next step we did was acid and heat. If we look at this guy, this is an ester, isn't it? If we dump in acid, we're going to hydrolyze that ester. That's all in the world we're doing. So step one is the bond that we made. Step one, we're going to take this acid hydrolysis, and we get this as our product. Simple acid hydrolysis of an ester. Everybody's happy with that, right? Step three, we look at this and say, well, wait a minute. This is a carboxylic acid, and it's beta to a carbonyl. Something in our mind tells us that that is special. That's what you need for decarboxylation. Anytime you have a carbonyl and a carboxylic acid beta to each other, we will decarboxylate. When we decarboxylate, we're going to lose this as CO2. Remember, the reaction is concerted, no intermediate. The acid simply pops off as CO2. There it is. And we're left with, oh my goodness, it's a diketone. So far we've done 2 of our 4 steps. We've done Michael addition of the anion to give the ester intermediate. We then acidified that hydrolyzed the ester to the acid. Because it's a beta keto acid, it decarboxylates to give CO2 and whatever's left. Any questions? Now let's take whatever's left and do our last 2 steps. This is the diketone that we just made. We're going to dump it into base, aren't we? Remember, if we have a ketone or aldehyde in base, we can do an aldol, can't we? Because they're both in the same molecule, we're going to wind up making a ring. So, let's rearrange this thing a little bit, and let's make an enol out of one of the carbons. Now we've done aldol condensations. We know that this anion is going to collapse. Electron density is going to attack down here. We're going to make our ring, and we're going to have a beta hydroxy carbonyl. We know that. Simple aldol, just all in the same molecule. That's what happens. And that's what we get. Now our final step, this was our aldol. Our final step was to add acid. Remember, beta hydroxy ketones and aldehydes dehydrate an acid, don't they? So if we take this, dump in acid, we're going to make a double bond here, conjugated with a ketone and that is our final product. So in our first two steps, we made the diketone. We then did an intramolecular aldol condensation, dehydration. The whole thing looks like this. And this is our Michael addition, hydrolysis, aldol condensation, and dehydration. Step one, our conjugate addition, the Michael step. Step two, hydrolysis and decarboxylation, beta-ketoacid. Step three, intermolecular aldol condensation. And step four, acid dehydration to give the alpha-beta unsaturated ketone. Any questions? All right. Pushing at the limit of being overwhelmed here. Let's just do a simple synthesis based on all of this. We're starting with cyclohexanone, and we're making this alpha-beta unsaturated carbonyl. Right? We just saw we can make alpha-beta unsaturated carbonyls from beta hydroxycarbonyls, right? Go ahead and draw the structure of the beta hydroxycarbonyl. Beta hydroxycarbonyl, well, here's the alpha carbon, that's the beta. All we have to do is stick the OH on it. See how I did that? There's our beta carbon. Now it's a beta hydroxycarbonyl. How do we make it? How do we make our final product? We just did acid catalyzed dehydration. All right. How do we start with cyclohexanone? That's this half, and make this. How do you make beta hydroxycarbonyls? An aldol. This is the bond we're going to make. This is going to be our enolate. This half used to be an aldehyde. Go ahead and draw the structure of the aldehyde that we need for our intermolecular condensation. The aldehyde simply had a benzene ring. This used to be a carbonyl. There's a hydrogen here. So this is benzaldehyde. Cyclohexanone plus benzaldehyde. Base gives us the beta hydroxyketone. Acid, we dehydrate. Let's use cyclohexanone and do another one. Here all we're doing is sticking an ethyl group on in the alpha position. How are we going to do that? We're simply doing an enolate at this carbon, using it as a nucleophile towards something else. To make the enolate, we're going to use lithium LDA. Going to take our anion, going to do an alkylation. The bond that we're going to make is going to be this guy. That means we need a 2-carbon chunk. All we're going to do is take cyclohexanone, LDA, followed by bromoethane. That would work. We introduce our simple alkyl group. All right, one more. We're going to take cyclohexanone. We're going to stick a nitrile down here in the beta position. Now, there's only one way in the world we know to introduce a nitrile like that, and that's through a Michael-style addition, isn't it? That means that we used to have a double bond here. Okay? So we're going to have to convert cyclohexanone into the alpha-beta unsaturated ketone. Then we're going to do a Michael addition to add the nitrile. Step 1, we need to introduce our double bond here. How are we going to do that? One of the very first reactions that we learned about enolates was that we could take a simple ketone or aldehyde in the presence of bromine and acetic acid and make it alpha bromo. Remember that one? First reaction we did with enolates. Once we have the alpha bromo, all we have to do is an E2 elimination to make the alpha beta unsaturated. For that, all we need to do is dump in a base. I used pyridine. You could just simply put base. That would work. And now we have our alpha beta unsaturated ketone. The final step is our Michael addition. All we need to do is add cyanide. HCN would work. Diethyl aluminum nitrile works much better. Boom, we have our product. Any questions? One more reaction I want to cover, or recover. Here we're going to convert cyclohexanone into an amine. The one way we know to do this is reductive amination. Now, reductive amination, if you ever watched Breaking Bad, is referred to as the biker method for making methamphetamine. Very, very simple reaction. It's the way a real organic chemist would do it. Not the incredibly dangerous stuff that they do, starting with, pseudoephedrine. But reductive amination. For reductive amination, all you're going to do is take a ketone, add an amine, and then a reducing agent. It's a secondary amine, and we're going to make this by a simple reductive amination. Again, we're going to start with cyclohexanone. The amine that we added was simply this guy, so that's methylamine, isn't it? Methylamine will add here, and we will form an imine, the intermediate imine. So a simple reaction with methylamine gives us the imine. If we do this in the presence of something like rainy nickel already has hydrogen built in. As fast as we form the imine, it reduces, and in one step, we make methylamine. The reductive amination step. Very, very happy, very simple reaction. Any questions? It's actually fun to look at the chemistry that is described in that particular series and compare the ephedrine method to reductive amination. Turns out that this is so simple that methylamine and the corresponding ketone, phenylacetone, are now regulated compounds by the drug enforcement agent, whatever that is. But you can't even buy this stuff without going through lots of hoops. Very, very simple reaction, though. Okay. Let's go ahead and do just a few more simple reactions. These are reactions of amines. The last chapter that we covered, remember, all of these reactions are basically just the amine as a nucleophile. In this case, it's acyl transfer. So is this actually, that our sulfur is our central group. This is going to give us a sulfonamide. Here we're going to make a primary amine from the allylic halide and phthalimide. Go ahead and write the products. Nitrogen is a nucleophile, and chloride is our leaving group. All we've done is make the amide. Nitrogen's our nucleophile, attacks the sulfur. Chlorine is our leaving group. We make the sulfonamide. Remember, this is a primary sulfonamide, and this hydrogen is acidic. Therefore, this stuff is soluble in base. This, you should recall, is our Hinsberg test. That if your sulfonamide is soluble in base, you have a primary amine. The last one, step one, the nitrogen is going to attack bromine leaves. In our second step, we're just going to hydrolyze the imide here, and we're left with a simple amine. Nice way to make simple primary amines. Another set of amine reactions. Our first one is going to be reductive amination. Our second is simply an SN2 reaction. Our third one, we're going to use azide as our nucleophile. Chloride leaves, get the acyl azide, very dangerous. When you heat it up, we're going to lose nitrogen. Phenylacetone is a controlled substance, but benzoic acid isn't. And you can make or easily convert benzoic acid into phenylacetone. All right, reductive amination, secondary amine is going to attack our carbonyl. Going to form an imine. It's going to be reduced, and we're going to wind up with our tertiary amine. The bond we made is here between our nitrogen, our diethylamine, and our ring. Make the intermediate imine, step 1, reduce it, just work it up with acid. Step 2, SN2 reaction. The nitrogen attacks the benzyl carbon, and all we do is a simple addition. Step 3 here, reaction 3. Azide is our nucleophile. Chloride leaves gives us an intermediate acylazide. That will lose nitrogen, and we make the amine. One more quick set. Our first one is one of our rearrangement reactions. It's an amide with base and bromine. Our second one, we're adding methylamine to an ester. Remember, nitrogen attacking an ester, that's the step that happens on the ribosome when you build a protein. Here we're going to take our amine in the presence of silver oxide, etc. Our first one, this is our Hoffman rearrangement. Remember, we simply lose the amide. Nitrogen moves over to where the carbonyl carbon was attached. We're going to add this, simply going to make an amide. This last guy is going to give us, following the Hoffman elimination, the alkene. Now, we actually knew most of the reactions of amines in chapter 24. The only one that was new was diazonium. We saw that we could take arylamines, aniline and aniline derivatives, in the presence of usually sodium nitrite in strong acid, and convert that to a diazonium. This stuff, these two nitrogens here, dearly want to be nitrogen gas. That's why it's so reactive. And you can take diazonium salts. If we use hypophosphorous acid, we said we could get rid of the diazonium altogether. These are called the Sandmeyer reactions. HCl copper chloride, we get the aryl halide, aryl bromide, or the aryl iodide. Again, these are the Sandmeyer reactions. There's one more on the other slide. The hallmark of the Sandmeyer is the use of copper 1, except for iodide. Copper 1 was Sandmeyer's contribution. And the other Sandmeyer that didn't make that slide is this guy. Again, copper 1, KCN. We can hydrolyze this off to the phenol. These two are very important dye-stuff reactions. Remember, phenols add to diazonium salts. Diazonium salts add to phenols, actually, at the 4 position, and we get coupling products. These were the things that originally led to the dye-stuff industry. If we do this with dimethyl aniline, we get this stuff that is brightly colored. It's some yellow dye. Any questions? All right, let's wind all of this up with a couple quick spectroscopy problems. As I'm sure you noticed, I hope you noticed, the rest of the labs are up. They're all integrated spectroscopy to serve as a review to get you ready for the final. Please make sure you get those things done. Start off with compound 1 here, C9H10O. That's going to give us 5 degrees of unsaturation. That means we're probably dealing with a benzene ring of something, and we have something else. We look at our mass spec. Our molecular ion here is 134. Our base peak is 119. I see a peak here at 91, but it's probably not a simple tropylium, is it? Why do I say that? Because if tropylium really can form, it's usually the base peak. So something else funny is going on. We start off with the molecular ion, we lose a methyl. That's about all we can really say. Look at the IR. Well, let's see. At 3400, I don't see anything big and broad and ugly that would be an OH. Here, just on the high side of 3000, I have a little peak, probably have sp squared CH. On the low side of 3000, I have something there suggesting we have sp cubed CH. Looks like symmetric and asymmetric stretching. If this was an aldehyde, remember we would have 2 peaks, but be around 2750. So it would be higher, we would have something in here, and we don't. So this probably is not an aldehyde. We do, in fact, well, we don't have a triple bond, let's say that, but we do have a very nice carbonyl here. Carbonyl at about 17, 10-ish, something like that. What this kind of looks like is, we also have these guys consistent with the sp squared CH2 and the degrees of unsaturation that would look like a benzene carbon-carbon bond. So that's this, this, this. Looks like it's a ketone and it has a benzene ring. NMR data. First, let's look at our proton NMR. Down in this region, we have 2 doublets, or 2 each. Remember, that's the hallmark for 1,4 substitution. So di-substituted benzene pair. We also have 2 methyl groups that are not next to each other or next to anything with a hydrogen. In our C13 data, we have a singlet here at 196. That's going to be a ketone carbonyl, isn't it? We have 2 singlets and 2 doublets. That's 1,4 disubstitution. And we have 2 methyl groups, which we saw here. So far it looks like we have an aryl ketone parasubstitution, and we have 2 simple methyl groups. How are we going to put this together? Well, we have our benzene ring. We know our 2 methyl groups are different. They're not next to anything with hydrogen, so they're singlets. and we have a ketone carbonyl. I think there's only one way you can arrange it, and that's to make this compound. 2 methyl groups are singlets, 1,4-disubstitution, ketone carbonyl. Let's do one more, and then we'll quit. I promise. C5H9O2Br. Again, doing our degrees of unsaturation, we only have one. Now, if we look at our mass spec here, this is our molecular ion, and it has 2 molecular ions separated by 2 mass units, and that's because of our bromine. Remember, bromine consists of 2 isotopes in equal quantities. Here we have lost, I don't know, something. But we still have our bromine attached. Here we still have the bromine attached. You know that because we have 2 peaks separated by 2, and then we get rid of our bromine to get down to the garbage. This is an M-45. Now there's only one common thing that we know that weighs 45, and that's ethoxy. So this suggests that we probably have an ethoxy group. Again, we have bromine in all of these. Don't quite know what this thing is yet. Our IR. The IR is kind of boring. We don't have anything in the OH region. Don't have anything on the high side of 3,000. We do have a peak at 2,900. We have no triple bond. But we have a really nice carbonyl here at about 1,750. We have nothing down here to suggest carbon-carbon double bonds. This just kind of looks like a simple aliphatic ketone. We also have a bromine in there, don't we? NMR data. In our proton NMR, we see a triplet and a quartet. They're leaning towards each other. This is screaming at you, I have an ethyl group. Okay? We have a doublet and a quartet. This is going to be a CH3, and this is a CH. They are leading towards each other. They are attached and coupled. So we have a CH3 next to a CH and an ethyl group. We already know that we probably have ethoxy to account for one of our oxygens. In our C13, this guy is at 172. Well, wait a minute. 172, that's not a ketone, is it? That's an acyl carbonyl. So we're probably dealing with an ester, not a ketone. This is a CH2, CH, and 2 CH3s. Same thing we said from here. All right, so it's an acyl ketone, or acyl carbonyl. It's probably an ester of some sort. We have a CH-CH3, and we have a bromine we have to throw in there. Well, this CH carbon is probably a decent place to put it. Here's our CH-CH3, Had to stick the bromine somewhere. There's our ethyl group and the ester carbonyl. All right, in 1 hour and 30 minutes here, we covered all of organic.
Why don't we just do that in the beginning?
We should have done it that way, right?
Start from the end, right?
And then we could have reviewed everything. All right. Any questions?